call is now being recorded. After we have seen a lot of problem types in optimization, I would like to mention about the very first thing, the most simple one, that is an unconstrained problem. I think we get this is a very well known from the calculus that when you have an unconstrained problem, the optimality condition is to take the gradient of the cost objective and set it to 0. And these optimality conditions will be solved a lot of times, not a lot of times, sorry. Sometimes it can reduce to linear functions, so you can have closed form solution. Sometimes this condition is still nonlinear, so you need a technique, a numerical method to solve these nonlinear equations. Okay. For unconstrained optimization, initially is a minimization, but the optimality condition becomes a nonlinear equation. Okay. Now, this is to make a very clear description that when you have a constraint, for example, this is unconstrained one, the least square problem. If you only add this one constraint when x is non-negative, okay. Very one first thing, the solutions is not the same, right? So the least square objective is convex. It has a paraboloid upward curve. Obviously, if you don't have any constraint, the bottom of the curve is your solution. But when you have a non-negative constraint, what does it mean? Let's just say that my cup is this. All right, this is my x1, this is my x2. So if I have add a non-negative constraint, is I have to look on this region only. So I look at how my surface. I want to look at the bottom part of my surface. That's still what correspond to this region. Okay. We're going to talk about, mathematically, what would be the analogy of this optimality condition for unconstrained problem. Okay. The optimal solution to the constraint problem is no longer satisfy this zero gradient condition. We're going to have more. We're going to have what's so-called KKT condition. Okay. That is optimality condition for constraint problem. Now, when you have a constraint, there are two types of constraint, right? Equality and inequality. Now I take a look at a more special case if those constraints are linear. The very first one is when you have linear equality constraint. So if I change the definition a little bit here, let's just pretend that, my x1 plus x3 is 0. This is linear equality constraints, which means the meaning is that, my regression coefficient, the one and the third one, they are coupled. They must abide by this constraint. But then if you take a look at this, and with the technique we have seen previously, the meaning of this is just variable elimination, right? Eliminate sum of x and write it again in terms of z. Easy example is this, right? When x1 and x3 must obey this equation, why don't you just write x3 as a minus x1 and put it back into cost objective, right? And now x3 disappear. It's going to be a function of the remaining variables. So that approach is called constraint elimination method. When you have linear equality, okay. When you have this is a typo. When you have inequality constraint, Now it depends on the form of inequality constraint functions. Okay. Of course, the simple one is going to be linear inequality constraint, something like this. So I leave it like we're going to have algorithm that takes takes the problem structure into account. Now let's talk about the theory a little bit because this is very important and very known as well. When you tackle an unconstrained problem, okay. Now let's assume that your f has a second order derivative is twice continuously differentiable. What does it mean? It is differentiable. How many order? Twice second order. All right, and then your second order derivative is continuous. That's what it means. Optimality condition in unconstrained problem have both necessary condition and necessary sufficient conditions. Review a little bit. When we have the statement P and Q, when you have a statement P and P then Q, right? If P is true, then Q is true. We say P is bunyalit. There are two types of conditions, necessary and sufficient. If the statement P then Q is true, we say P is sufficient or necessary for Q to happen. P is a sufficient condition for Q, all right? And we say Q is necessary condition. Why do we call Q is necessary? Because this equivalent to not Q, then not P, right? Q is necessary because whenever Q doesn't hold, P cannot be true. Okay, all right. Now if we look at statement, it's going to be we're gonna exercise a little bit about like all the two types of conditions involved in unconstrained. First of all, when we say first order condition, it means that those conditions involve the first derivative. Second order means those conditions involve Hessian matrix, the second derivative of your function. First of all, this is very simple. First order necessary condition. If x is a local minimizer of f, then that x satisfies the zero gradient condition. The zero gradient condition is a necessary condition for x star to be a local minimizer, right? Now, we have second order necessary condition as well. Look at the statement. If x is a local minimizer, and then x must satisfy the zero gradient, and the Hessian is positive semi-definite. The zero gradient condition and the positive semi-definiteness of the Hessian are necessary for x star to be a local minimizer, right? อาจารย์งงนะ okay these two conditions serve as necessary condition for optimality of x star. Now remember in the basic calculus that you have learned before, suppose the function is nonlinear. If I ask you, can you find a local minimum and verify that it's a local minimum, the very first thing is you're going to find all the points that have zero gradient, right? And what's the next step that you want to check whether it's a local minimum or not? Check the second derivative, right? And evaluate it at those x, right? That second derivative must be non-negative, right? And that's how you claim. And for the local maximum, that secretive is this negative, right? This is the same thing. This is same thing here. I'm gonna state the sufficient condition. Now, take a look. The zero gradient and the positive definiteness of your Hessian matrix are sufficient condition for concluding that X star is a strict local minimizer of F. Okay, so these, right, just like you have in the calculus. You find all the zero gradient points. I think I'm going to have the name later. These are called stationary points. And then examine the not the sign, the positive definiteness of the Hessian. Ah. Now, with that conclusion, you can say the same message to unconstrained maximization problem as well. Okay, because we know that minimizing F is maximizing minus F. So for the second order conditions, for the necessary part, if X star is a local maximizer, then it must have zero gradient and the Hessian must be negative, semi-definite. Because of this, right? I mean, the Hessian of the gradient of minus F is the minus gradient of F. Very straightforward. For the sufficiency part, if it satisfies zero gradient and if the Hessian is negative definite, then it is sufficient to conclude that your X star is a strict local maximizer. Okay, now let's get some name, all right? All the point that satisfies the zero gradient condition is called a stationary point, also known as a critical point. Okay. A stationary point may be a local minimizer, may be a local maximizer, or neither of them. Remember, a matrix can be positive, definite, can be negative definite, or neither of them, indefinite, right? Indefinite. I mean, this doesn't happen to a scalar function. If F is scalar, it's just two cases, right? Either the Hessian is non-negative or negative, right? But for matrix, you have indefinite case. A matrix is indefinite when eigenvalue of this matrix can be plus and minus, positive and negative. If a stationary point is neither a local mean nor a local max, it is called a saddle point. We have some example here. We're gonna use this function as a test function for a lot of time. This is called Rosenbrock function. It's in your homework this week as well with different coefficients. So it's a function of two variables, x1 and x2. Okay. These coefficients can be varied. All right, can be varied. I think when you do the homework, actually in the homework, I'll ask you to plot the contour of this function and see where the minimum is. Okay. Now, and compare with the result that you do analytically. Verify. Can you just verify the Hessian and the gradient? Sorry, the gradient and the Hessian. This is a function of two variables. The gradient is 2 by 1. Hessian is 2 by 2. I still. This is del f by del 1, del f by del 2. This is what? Take the gradient respect x1, take the first component of the gradient respect x2. Hessian has to be symmetric. If these guys are not the same, you take the derivative incorrectly. Okay? No? Yes. The Hessian has to be symmetric. This is what? This is the second component of the gradient with respect to x2. Okay, just verify, not hard. Okay, when you solve the stationary point, so you set it to 0. You set it to 0, and then you can play with the equations. Oh, so that only occur when x2 is x squared, x1 squared. You plug it back into the first equation and solve it. You will end up that I find only one stationary point, which is 1, 1. Which is 1, 1. Now, I'm going to apply, right? I'm going to apply to these necessary and sufficient conditions. So I'm going to verify the second order derivative. I plug it back into this Hessian and then found out that this Hessian matrix at 1, 1 is what? Positive definite. How can I check? Huh? Yeah, for 2 by 2, right? For 2 by 2. So the idea is that, of n by n, if a matrix is positive definite, all the leading blocks must be positive semi-definite. You can check all the principal minor, the determinant of all the leading blocks. Okay, so obviously for 2 by 2, you just check, oh, this is positive, and then check the determinant. Okay, of course for n by n, and when you have the data, from the data you just compute the eigenvalues. So by what? By sufficient condition, you have found a stationary point where the Hessian is PDF, so you can claim that this is a local minimizer. But because there's only one stationary point, so that is the only local minimizer you can find, right? Now with this result, just plot the graph and everything, and then I think in another class of mine, in 511, we're gonna see, if you take a look at the contour, try to pay attention to the shape. Sometimes this is called banana function. Banana function. See the contour and locate the minimum, the local minimum, and maybe just look around why Rosenbrock function becomes like a benchmark, becomes like a test bed of many algorithms. In this, I also have another example of a saddle point. Again, this is a function of two variables. If you again solve for a stationary point, you found only one stationary point, which is -4 and 3. And then when you check the Hessian, obviously the Hessian is diagonal. The diagonal are mix of non-negative and negative values, so the Hessian is indefinite. So that stationary point is neither a local mean nor a local max, and then it is called a saddle point. So this is the saddle point, and this is how it looks on the contour. What's the meaning of the second derivative? The second derivative is a rate of change of the first derivative, right? So if the second derivative is positive, it means the gradient is increasing or decreasing? Increase, right? And when the Hessian is negative, the gradient is decreasing. When the second derivative is 0, the second derivative is the rate of change of the gradient. When the second derivative is 0 itself, the gradient doesn't change. right? Okay, now this is the last part. We have talked about property of unconstrained problem. Now I think it's quite now we're quite comfortable to take a look at one example of unconstrained problem. We have seen this problem a lot in applications. Nonlinear least square. This is a specific form of unconstrained problem. In application, we always encounter something like this. Oh, you have data point, the blue points. You want to fit a curve parameterized by some mathematical expression. In this example, I want to fit a Gaussian curve. Gaussian curve, how can you recognize it's a Gaussian curve? Exponential of negative quadratic. Okay, these Gaussian curve, they have three parameters. They have A, they have B, they have C, they have D. Okay, I hope you can relate the role of these parameters. So when I change B, what happened? Translate, right? Translate the Gaussian curve on the x-axis. What happened if I change C? If C is bigger, more like wider spread, right? D, shift the Gaussian curve on the y-axis. A, huh? Just radically increase the magnitude of the Gaussian curve. So go back and again. I have three Gaussian curves: the purple, the orange, and the yellow. Okay. How the parameters of the Gaussian curve in these three curves are different from each other. All right, that's not hard. So in optimization, if you take a look at the problem, I want to pick a set of parameter A, B, C, and D that makes the error between what? The error between the curve to the data point. I want this error to be sum square and then minimize. This is the concept of nonlinear least square. Which one should be the one with a smaller objective, smaller error? Yellow, orange, purple. Orange, right? So the question is, how can you? I want to end up with something like this, right? How can you pose it as an optimization? Nonlinear least square is a problem where you have a data point and you have a form of function. So if you translate it sorry, I skip it. Okay, nonlinear least square is a problem where you come up with a specific form of function g, yi are given. So yi are given. The structure of g is given. Just like previously, I specify my curve to be Gaussian. But this g, a lot of time, this g has a parameter. Just like I have those ABC, right? Then, so this is a function of theta, all right? Sorry. Oh, yes. This is a function of theta. I want the sum square error to be minimized. So so for interpretation, we use the term Ri as a residual between Yi and Gxi, the error of one data point to the curve. Okay, and what we do is sum square and then minimize. I put 1/2 here, just a matter of convenience when we calculate the derivative. Okay. This is just to express the problem description. Okay, in applications, I can change G to be other things. All right. What else? Trigonometric function, other exponential function, other exponential family. when when my g when my g x theta, when this guy becomes linear in theta, that reduces to linear least square. Again, so what I'm trying to say is in nonlinear least square is an unconstrained problem with a specific form. Okay, in terms of algorithm, there's dedicated algorithm for that. Okay, so in the process of solving this one as an applied user like us, it just it's just a matter of formulate your problem in terms of this nonlinear least square form. For example, previously we have seen a problem of minimizing Rosenbrock function. This one. How can you represent it as a nonlinear? The very first thing, oh, is this a nonlinear least square or not? All right. If it's this type, you can just use the dedicated algorithm for this problem. This one, if you take a look, it is the same thing as, oh, I have the residual vector R1, R2, the dot RQ, right? And the sum square is the same thing as the norm of residual vector squared, right? The terms nonlinear, it means that this residual, this R, is a nonlinear function in X. If you come back to this notation, not if it's nonlinear, it means this residual is nonlinear in theta. Do not get confused between, this is X in terms of optimization problem. In this one, I try to explain that nonlinear has seen a lot in application as a curve fitting problem. With this standard notation, the optimization variable is theta, the parameter of the curve. In the context of curve fitting, the variable x is the data point on the x-axis. Okay, not x in our optimization. Like your theta here is the x in minimization. Quick exercise, and then we have to finish it for this lecture. Minimization of this, is it a nonlinear least square? Can we represent it as that? Can we represent it as the sum square of some function? What is our R? First of all, you recognize that it's a sum square of two terms, right? Right? Square of what? It's square of obviously square root 10 x2 minus x1 square, right? And then the other term would be 1 minus x1, right? Right? So minimization of this is the same as, can be arranged as nonlinear least square of this sum square of this vector value function. Okay. Just a matter of arrangement. Or maybe I need to.
Ax plus b, which must be done y is equal to x plus b, and then from 1 again minimizing the error first variable and the save here like y of I minus g of x of I.
Mm.
So you mean that we need to differentiate the objective function in order to check whether the function is nonlinear or linear.
Okay. Previously we say linear regression in this format, right? Y minus ax. Again, this is a minimization over x. Okay. And it's going to be the same thing as summation I over n yi minus ai transpose x squared. If I replace this as theta, you don't get confused, right? It's just optimization variable. I'm trying to say that this is AI transpose theta. This is your one special case of a curve that is linear in theta. So this is a problem of, oh, can I approximate y data points as a linear function that has a slope of a, okay? Now, because I can make it more general, right? I enlarge a set of curve fitting candidate. So if I replace it as g as a function g, right? But I mean, obviously, your function depends on your x. This x is not optimization. This x is a coordinate of your data point in x-axis. But this function has a parameter of theta. When you generalize it in that way, I'm saying that when the error between data point and your functions, now I don't look at y and x, right? I look at y and x as pre-specified values because those are data, they are given. Now I'm going to look at the residue, at the error as a function of theta because I'm going to minimize it. Okay? When this residue becomes nonlinear in the parameter, in the optimization variable, and you want to minimize the sum square of the error, the problem is called nonlinear least square. And what I want you to practice like representing the problem in a nonlinear least square sense, like how can you recognize a residual vector or not? Because as an apply user, we're gonna call algorithm, we're gonna call the library, and the format of calling is just to specify a vector R. Of course, obviously you may have question like, what are we gonna do with this? Are we gonna take the gradient, set it to 0, and then we solve it or not? Yes, the algorithm, I mean, of unconstrained problem, try to solve it that way. Try to solve it in such a way that you have reached the optimal point that satisfies the scene. So maybe, yeah. If I click the entire screen, share now. This is the what? This is what? Which screen? Ah. If eh? Ah. Is it on screen? I need to share now. Okay. I'm gonna actually at the end of our at the last week of our lecture, we're gonna demonstrate some of the tools we can use in MATLAB. Okay, so I'm trying to say that of course what you see on what do we see on the slide right now is what? Eh? This in how can I oh stop, how can I share the screen on the desktop? A window. Okay, is it what? Because look at your slide, the nonlinear least square is actually a unconstrained problem as well, right? So But it's just an unconstrained problem that has a very specific form, sum square. So in terms of solving it, you have two available tools. For example, this is a command where you solve unconstrained function, unconstrained minimization. But because you already know that it's non-linear least square, you can also use a command like least square nonlinear. But the way you put the problem description is going to be different, because this one, you want to minimize fx, just give me the fx. All right. But for the nonlinear least square, it had a structure of sum square, right? So you don't need to tell me that is a sum square. Just tell me the vector r. Got it? So when you call an algorithm that solves nonlinear least square, the input is just give me the r, the vector r. So it's as simple as that. All right. So when I call this, I didn't put the sum of ri square. The sum square will be handled by the command itself, because it is designed for that purpose. So if you look at the description, is it on the screen? Right? The nonlinear least square is just the sum square. So you just, as a user, you just put the vector f, which is our vector r in the slide. So that's why it's just a simple exercise that I asked you. Oh, can you write the minimization of Rosenbrock as a nonlinear least square problem? Okay. So that's about it. That's for unconstrained. I think in the homework, even though that we're gonna demonstrate some tools at the last week, but I think you can explore this as well. All right. Maybe try to minimize the Rosenbrock function. Usually you need to put a function and initial point. We're gonna talk in the fourth week. Why do we need an initial point? How can we choose it? But I think right now, just to get to see how it does. I mean, it can be a bad choice or a good choice. Just try. All right, just try. Minimize description of Rosenbrock function, some initial point, and then because you already know in the math that local minimum is at, in the slide, is at 1 1, and see if your return solution is correct or not. Okay. Is stop presenting.